Physics of Interstellar Travel. Chapter 16, Payloads. To do anything useful, our robotic spacecraft needs to take scientific instruments with it. In this chapter, we take a look at what kind of instruments there are and what we can learn from their measurements. We also consider possible sources of powering the spacecraft. Finally, I discuss the benefits of sending a swarm of spacecraft rather than one individual spacecraft. This diagram from ESA shows the instruments on the Jupiter Icy Moons Explorer, JUICE, which will arrive at Jupiter in 2031 to explore the three large satellites Ganymede, Callisto, and Europa. JUICE serves as an example of the kind of instruments we may want to have on an interstellar spacecraft for exploring a distant star and its planets and moons. It is unthinkable that we would send an interstellar spacecraft and not equip it with a camera to take pictures. A visible UV and near-infrared camera would be used to map the surface of a planet in reflected starlight. This camera, or these cameras, would also be used for navigation within the star system and for searching for planets and moons. Mid-infrared cameras can look for thermal emission from the planet. We discussed in Chapter 2 the enormous gains in spatial resolution and light-gathering power that an in-situ spacecraft gives over Earth-based observations, as well as the ability to change observing perspective. Visible UV and near-infrared spectroscopy is key to determining the chemical composition of both planetary atmospheres and their surfaces. Instruments can be optimized in wavelength coverage and resolution to identify certain features, such as atmospheric biosignature gases or surface vegetation. Submillimeter spectroscopy is particularly useful for investigating the structure and dynamics of the middle and upper atmospheres. Observations of exoplanets from the Earth are limited to collecting photons. An interstellar spacecraft, in contrast, can also measure atoms, ions, and molecules directly using a mass spectrometer. Particle detectors could also allow the spacecraft to directly sample the interstellar medium en route. Dust particles reveal much about the surface composition of rocky planets. Although JUICE is not equipped with a dust instrument, its partner spacecraft, NASA's Europa Clipper, which will arrive at Jupiter about a year earlier, is. Magnetic fields can tell us about the internal structure of planets. Interestingly, variations in Jupiter's magnetic field induce electric currents in the suspected saline ocean below the icy surface of Europa, which in turn create magnetic fields. Measuring these will allow JUICE to characterize such oceans. JUICE is equipped with a second instrument to measure not only magnetic fields, but also electric fields. The instruments mentioned so far were passive. A LiDAR, an optical radar, in contrast, bounces laser pulses off the surface of a planet. By measuring their travel time, it can accurately map the surface at high resolution. This can be used to identify shallow craters caused by volcanism or asteroid impacts. Similar in principle to LiDAR, low-frequency radar is able to penetrate ice layers many kilometers thick. In the case of JUICE, radar will be used to map the thickness of the ice covering its oceans. Now, probably not all of the types of instruments mentioned here for JUICE would be deployed on a first interstellar spacecraft, but this gives some idea of the kind of measurements we can and may want to make. A spacecraft needs power for its scientific instruments, its navigation and control devices, and for communication. Instruments on current solar system probes typically need between 1 and 10 watts of power each, but extreme miniaturized instruments, as required for low-mass laser sails, for example, would require much less power. Communication takes as much power as it can get. Typically, planetary explorers in the solar system have used a few tens of watts for communication. Many satellites, and increasingly even solar system explorers, use photovoltaics, that is, solar panels, as a source of power. 1 astronomical unit from the Sun, these can provide about 400 watts of power per square meter. It takes into account their finite efficiency. This power drops off with the distance squared, so photovoltaics are no use during an interstellar journey. But they could be used during flyby or once a spacecraft goes into orbit in the target system. If the spacecraft has nuclear propulsion, it would be possible to use this to generate electricity for onboard power. This would constitute a tiny fraction of the power needed for acceleration and/or deceleration. Current commercial lithium-ion batteries are able to store about 1 megajoule of energy per kilogram of battery mass, equivalent to 300 watt-hours per kilogram. The best batteries can achieve only 3 times this, so they are really no use as a primary energy source, although they could be used as a backup over short periods. Capacitors have much lower energy densities even than batteries, so their role, if any, would be limited to power regulation or backup. A fuel cell extracts electric current from the reaction of hydrogen with oxygen. The combination of hydrogen and oxygen has an energy density of about 13 megajoules per kilogram, which is higher than batteries, although we also need to take into account the mass of the machinery of the fuel cell itself. Fuel cells were used as one of the power sources on the space shuttle, delivering about 7 kilowatts of power. But one of the most effective power sources for deep space vehicles has been the radioisotope thermoelectric generator, or RTG. This contains radioactive plutonium-238, which decays by alpha decay. The alpha particles heat one end of a conductor, the other end of which radiates heat to space. The resulting temperature gradient along the conductor generates an electric current via the Seebeck effect. RTGs have been used on many interplanetary spacecraft, such as Voyager, Cassini, New Horizons, and some of the Mars rovers. We see here the RTG on New Horizons. It's the black cylinder sticking out to the left and is just over a meter long. This RTG contains about 11 kilograms of plutonium dioxide and provided 245 watts of power at the start of the mission. As the half-life of plutonium-238 is 88 years, the power dropped by about 7% in the 9.5 years between launch and arrival at Pluto. For an interstellar mission lasting 50 years, the power would drop a lot more, but could be designed to be sufficient for that mission. Although we have not considered the economics of different propulsion systems, it seems clear that for laser sails, much more investment will go into building the kilometre-sized optical arrays and lasers than into a single sailcraft a few meters in size. It therefore makes economic sense to build many sailcraft. As the acceleration times are short, minutes or hours, it would be possible to launch many sailcraft in a short space of time. Given the extreme mass limits of sailcraft, this gives us the opportunity to spread the scientific payload across many spacecraft, each fulfilling just a proportion of the mission. Such a swarm of spacecraft could also be designed to have a cross-spacecraft redundancy, just in case some of the spacecraft are destroyed en route, for example by large dust grains. If the spacecraft are smart and can communicate with each other, they could even optimize their collective science return. For example, later arriving spacecraft could study interesting phenomena discovered by earlier arriving spacecraft in more detail, or redo failed observations. More advanced interstellar spacecraft might one day carry smaller spacecraft that disperse to explore the star system in parallel, or even deploy rovers that land on the surface of an exoplanet. But I'll leave that to your imagination.